Hey, how are you guys? Let me start now. Okay, while the others are still joining the meeting. Okay, in parallel processes, in this chapter, we are interested in understanding, okay, the time, okay, and time parallelizable, that means, and the sequential of, okay, when we use more than one processor. Like in general, okay, if I want to understand while we are using a single processor, okay, it means we are going to a sequential execution of instructions, okay? Is that all right? However, in parallel, okay, in parallel processing, okay, so in this case, we are working on many, okay, more than one instructions and simultaneously. Okay, that's the reason why we talk later on about the threads and multi threads. Okay, and in this formula, okay, in this formula, we can see the new, okay, time for, because there's some instructions or some set of instructions can be parallelized, and some of them still we have to keep them sequential. Okay, so the total time in this example, okay, so in this example we have 100, say for example we have 100 processors, okay, 100 processors. For the portion of the code, okay, portion of the code can be parallelized, okay, then can be divided into 100, and another portion of the code of the code, okay, can be stays as a sequence of instructions. Okay, so what I need from you in this chapter is to get to understand these two formulas. Okay, so how to find the speed up? Okay, it's 1 over 1 minus f, okay, the portion parallelized, okay, plus f parallelizable over 100 equal 90. So how to find it? Okay, solving f parallelizable. Okay, so we have one equation, okay, one equation with one unknown. Okay, so 1 over 1 minus, okay, the ratio of, okay, the parallelizable, okay, plus f parallelizable of 100 equal 90. 90 is given, okay, and the 100 is the number of the processors, also is given. The 100 processors is also, we call them that when we see them, so the amount of improvement. Okay, so in this case we obtain 0.99, which is approximately 0.1, okay, percent of original, okay, of original time. Okay, because if we this one, if we divide by 100, okay, they should be equal 0.099, so approximately 0.100%. Another way of using this formula is to get the time of, okay, this is an example. We have workload, we have sum of 10 scalars, okay, and 10 times 10 matrix. So the speed up from 10 to 100 processors, okay, it can be like this. The time is for the 10, okay, 10 scalars, okay, I mean 1 by 1, and the matrix is in parallel. It's 100 times the time of addition, okay. So the time is 10 times TAD and 100 times TAD, okay. All right, so we have it, okay, because this, the 100, okay, on 10, okay, processors, so we divided by 10, okay, so the time is equal to 20 TAD, okay, so 20 times of the addition of the time. Okay, so this how to calculate the speed up. If we take them as ones, it means 110 times 10, okay. So when we add, okay, 10, okay, 10 processors, when we add 10 processors, okay, the times change to 20, okay, instead of 110, it changed, if we see in 110, it changed to 20. It's 5.5, Okay, how to calculate the percentage? So we multiply 5.5, okay, times 100 divided by 10. 10 is the number of the processor we have it, okay, in here. All right. So we obtained, okay, 55% of potential, the speed up, okay? So this is, you have to retain this formula, okay? So the given should be like this, okay? Scalar and matrix, okay? So you divide them to make the sum for both of them. This is the scalar, okay? And this is the matrix, 10 times 10 is 100 over 10 times the t, okay? So this is the total time. So this is the original. The new obtained is 20. So say, for example, in this case, we are working on only 10 processors. If I'm working now on 100, okay, processors, that should be changed. Is that okay? 10 times 10, 100, okay, over 100 times t equal 11, okay, t 80. However, we can see in here, okay, the speed up is 110, which is the total, okay, the total is 110 divided by, okay, 11 equal, okay, 10 equal 10. Then how to obtain the percentage? 10 multiplied by 100 divided by 100. Cancel these two guys. We have 10%. Okay. So this is how we calculate, okay, the speed up. Okay. And we can see here it's 55% of the potential. Now it's 10%, only 10% of the potential, while we are increasing the number of processors from 10, okay, to 100. Okay, but we have low percentage in here. So assumes the load can be balanced across, okay, processors. Let me show you. So what if matrix size is 100? It means 100 times 100 is 10,000. And we have 10 in the scalars, 10 plus 1,000. We have 10 processors. Okay, we keep the same one as it is, 10 times the time of the addition. Okay, 10,000 over 10 processors times something, we obtain 1,010 times the 80. In comparison with the first one, which is 10,010, okay, divided by 1,010, we obtain 99% of the potential. Okay, so how we obtain 99%? As I said, 9.9 times, okay, 100, okay, divided by 10, so we obtain 99%. Okay, so only in here we have only these two formulas. What I need from you is to concentrate on them. So the given can be like this in scalar, okay, and in matrix. Then we find the speed up using this way. Okay. If we have 100 processors, the same formula, but instead of 10 here, we replace it by 100. Okay, we have 110 and 1,000. 10,010 of 110, we obtain 90%. Okay, we have 91%. Yes.
Why are we not dividing the number of scalars كمان؟ ليه بس الماتريكس؟
لا انتبه. أنا when I said in the beginning, okay, في عنا portion of the code can be parallelized, or portion of the code بيضلوا cannot بيكون sequence. Okay.
اوكي يعني الماتريكس it can be parallelized،
هي
بس
هذا البارت هو okay parallelized. Okay. However, the first part, يعني نحن okay, when we have 100 times 100, we have 10,000. هدول 10,000 will be executed simultaneously on 10 processors. Okay. يعني حيكون in parallel. Okay. في عنا نحن لما يكون في عنا more than one processor عم بيصيروا بنفس الوقت، حياخذوا نفس الوقت كلياتهم، صح؟
ايه اوكي فهمت. ميرسي.
فمشان هيك نحن if I refer, let me go to the first part of the first slide. عم نشوف في عنا portion بيكون بستay sequence، اوكي، وportion بيكون parallelizable. اوكي، فمشان هيك اللي بيكون هو in parallel فوي divide بنقسمه نحن. ما نحن شو معناتها in parallel؟ معناتها we are working simultaneously on more than one processor. Okay, معناتها we divide the tasks into the number of the processes that we have اللي هو بنسميه احنا احيانا كمان number of improvement. Okay. يعني نحن if we notice in here we have these two formulas. Okay. And if we give you the speed up, we are able to calculate this value. And in another way, if we have the number of the processes and the tasks that can be taken, we are able to find the speed up using this one. Okay, the original divided by the new time in here. Okay. And if I continue in here in the same example, we notice in here we have improved 99% of the potential, 99%. In here, why we obtained like this? If we have this for 10 processors, okay, we have speed up 99.9. For 10 processors, 9.9. Okay, 100%. So we multiply. Okay, then we divide. Okay, this is how we obtain it. 100 times 9.9 divided by 10, we obtain the percentage. Okay, when we replace the 10 processes by 100 processes, okay, we can notice also the speed up, okay, decreased by about 7% or 8% to 91 percent. Okay. Strong scaling problem.
دكتور بس دقيقة فيك ترجع على السلايد اللي قبله.
يلا.
كيف في شيء غلط بالبرسنتجز إذا فوق 9.999 وتحت 91 في شيء غلط. 91 المفروض تكون 910 يعني.
لا انت عندك هون 100 انتبه.
ايه بس كيف ال 9.9 فوق؟ انت عم تقسمها على حالها كبروسيسور يعني.
لسه انت لما تكون عم بتطلع على البرسنت.
اوكي
هرجع اعطيك in general.
I got it خلص.
اوكي البرسنتج هو x times 100 divided by n هو النمبر of the processes. اوكي يعني خدها انت بهالطريقه هيدي. اعتبر ال 9.9 او 91 اوكي هي x على طول multiply by 100 and divide by n اللي هو number of processes can be 10 can be 100 can be. Okay, that's how we obtain the percentage. Okay, is that clear? Yes. Okay. Strong scaling problem size fixed as an example. Give me a weak scaling problem size. لما يكون عندنا weak scaling لما both of them change the size of problem size proportional to the number of processes. Processes sorry. مثل هون في عندنا احنا the problem size one number of processes. When we increase the problem size, the number of the number of processes also increased. بنلاحظ نحن بيكون في عندي 10 طلع 20 ونفس الشيء لما صار عندي 100 32 كمان طلع 20. هلا we can make the calculation for it. Okay. I want to show you also, if I go back to the textbook, let me share with you the textbook. For further explanation, you can refer. Okay. In the textbook, the chapter 6, okay, so we can, if you want to read more, so you can go through. Can you see chapter 6? Okay. Yes. Okay, so these examples are here in more details. I have them in chapter 6. And also the examples in here: strong scaling, weak scaling, okay, speed up balancing load. All right, and also different types. Okay, parallel hardware proposed. Okay, I'll go through this part. In all the slides covered, okay, and covered from the textbook. Okay, so you can refer to the textbook for further reading. Let me continue. Okay, the instruction streams and data streams. Okay, let me go through instructions and data streams. Okay, for example, SID means single instruction, single data. Okay. SIMD, it means single instruction, multiple, okay, multiple data. Okay. MISD, multiple instruction, single data. Okay, but the most complicated, most used for parallelism and with the GPU is this part. Okay, multiple instructions and multiple data. This is the type of processor that we can have. Okay, let me show you. Let me go to the for vector processors. Okay, also in the textbook they explain about vector processors. And vector processor, because while we are working in there's a scalar processor and vector processor. Okay, in scalar processor, it means we are working with the single data. Okay, so while the vector processor, okay, can be used, okay, for the vector processor can be used for better, okay, for example, parallel processing. Okay, if you're using graphics, more graphics for multimedia, okay, because it can allow the processor to access, okay, more than one location of data at the same times. Okay, it means, so if we are working in parallel processing, okay, we go for vector processings that can manipulate, okay, more huge amount of data instead of scalar. While scalar, we are accessing only single data. Example vector extension, okay, to like the 832 times 64-bit, okay, elements. Okay, so we are able also, there is some instructions can be used for the vector, how to load and store in vector, add vector, okay, of double, add the vectors, okay, to element vector double. And just want to let you know at this stage, okay, for me in a part of the calculation and the formulas, please make sure you remember this formulas in here. Okay, it's only two formulas, the one for the time and one for the speed up. Okay, make sure you remember all this, okay, for problem solving, while the other content of this lecture is only based on theoretical. Okay, so it can be only theoretical, since you are not going to do parallel coding. Okay, just I want you to understand the difference between a scalar processor, okay, vector processor, okay, different types. Okay, the architectures, okay, as I said, the simplified data parallel programming, the vector architectures, explicit statement, okay, of absence of block carried dependencies, okay, reduced checking in hardware. Okay, so what I want you only to get some definitions from the other slides, okay, about, okay, what we're talking about. A single instruction, multiple data, operate element-wise on vectors, okay, of data equal MMX and SSE instruction in, okay, x86 process, multiple data elements in 128 wide registers. Okay, all processors execute the same instruction at the same time. Okay, so in this case we are talking about, okay, parallel, okay, processing using multiple data. Simplify synchronizations, reduced instruction control hardware, and works best for highly data parallel applications. Okay, yeah, this is for the multimedia vectors versus multimedia extensions. Okay, as we can see in this part, okay, vector instructions have a variable vector width, multiple multimedia extension have a fixed, okay, width. Okay, as we can see in this part, we have only a single pipeline. Okay, vector units can be combination of pipelines and array functional units. Okay, as we can see in here, like the vector units can be combination of pipeline, so we can execute in the same times. Okay, so multiple addition. Can you see in this part? okay, we can execute more than one, okay, pipeline. However, in this part in here, we have only one, okay, pipeline. Okay, so that's why within vector units can be combination of pipelines. Okay, combination of pipelines. So multi-threading. Multi-threading can be also appear in two ways. Okay, well, so when we execute, okay, more than one task, and there's some synchronization between them. Okay, so with multi-threading allows the execution in parallel. Okay, replicate registers and program counter, fast switching between threads. Types, we have fine-grain multi-threading, and we have coarse-grain multi-threading. The fine-grain multi-threading switch threads after each cycle. Okay, interleave instructions execution. If one thread stalls, other are executed. نعرف شو هو الستولز ما هي؟ If one thread stalls, شو معناتها؟ If one thread stalls, it means لما بيكون نحن عنا البروجرام بينقطع, okay, stop at some at certain stage. Okay. مثل ما حكينا المرة الماضية في عنا الستولز, في عنا الميس. Okay, لما يكون في عنا data waiting for another data to be calculated أو obtained. Okay. بنشوف بيصير في عنا stall للبروجرام. Coarse-grain multi-threading only switch on long stall. Okay, add to cache miss. Okay, simplifies hardware but doesn't hide short stalls. Okay.
دكتور بس سؤال.
تفضل.
لازم انه نعرف fine grain multi threading شو هي و coarse grain multi threading
أنا
شو هي
I want
أو
you only to get through only as I said بهذا lecture, in this lecture the first part هو more في عنا application على الformulas, and the last part في عندي بس يعني just to understand definitions. يعني if we ask you for true false يعني so you have to just remember the definitions about it to understand what they are they. يعني ما بدي أنا go in more details in them. Okay, just to understand the theories behind the other slides. Okay, as I said, you are not going to do a parallel programming. Okay, just I want you to get the definitions of them. Okay, so in multiple issue dynamically scheduled processor schedule instructions from multiple threads. Instruction from independent thread execute when function units are available. Okay, within threads dependency handled, okay, by scheduling and register renaming. هلا انا بدي اوصل لهيدي الدايجرام هون بنشرح اكثر. اوكي, بالمالتي ثريدنج عم نشوف في عندي two types. في عندي هيدا البارت, اوكي, بنشوف في عندنا blocks in black and blue and gray, okay, and clear blue, light blue, sorry. Okay, بنشوف with the time, with the clock, okay, while the clock clicks. Okay, في عندي thread A, thread B, thread C. Okay, each one of them, okay, execute, all right, a specific thread by itself. Okay, same type, same colors, same blocks. Okay, however, and the other one with the fine-grained multi-threading under course. Okay, بنلاقي في عندنا in the same time, okay, في عندي combination of thread, مشان هيك عم يصير في عندي multi-thread, okay, can be done within the same time. Can you hear me? Are you still with me?
Yes,
yes.
Okay, لأنه I think yes, في عندي is still 10 minutes, 9 minutes. Okay. لأنه Zoom, I think it's 40, only allow 40 minutes. Okay. But what I'm trying to tell you, let me share with you the textbook in here. Okay, in the textbook, شوف هون في عنا okay, only one, okay, using multiple functional units to improve performance. A single vector as instruction sequence, the vector processor A on left hand side. Now نشوف هو single and pipeline, single add, so we can use only one single add. However, in part B, okay, في عندنا 4 add pipelines. نلاحظ okay في عندنا 1 2 3 4, okay, and can complete 4 additional per cycle. Okay, see the difference between them. Seminal vector lanes. Okay, all right. Also, in this case, okay, how 4 threads use the issue slides, okay, of a superscalar processor differing the form كما نشوفوا نحن هون فوق. Okay, the 4 threads at the top show each, okay, would execute running alone on a standard, okay, superscalar processor without multi-threading support. Okay. However, but the second part بيصير عندي أنا multi-threading, okay, multi-threading support, وبنشوف الcolors اللي هن كل واحد بيدل على different, okay, different thread in the same times. Okay, بنشوف هون ما في multi-threading. Okay, but the second part محل في عندي أنا course, okay, multi-threading, fine multi-threading, okay, كلهم صار موجود. Okay. As I said, I want you only to understand, okay, the theories behind it, okay, definitions. Okay, and if we ask you for multiple choices of true, false, so you can answer the questions. Okay, what I suppose on you, okay, when you go through the lecture, the PowerPoint slides, okay, إذا في محل في definitions, please make sure you read and understand definitions behind, okay, topics, and also where we use some problem solving, you have to get back to the problems we solve them in the class and to do revision for them. Okay. Feature of multi-threading. Okay, will it survive? Okay, in what form? Power consideration, simplified, okay, microarchitectures, simpler forms of multi-threading. Tolerating cache means latency. Okay, a thread switch may be most effective. Multiple simple cores, okay, might share resources more effectively. Okay, so we remember later on when we talk about, okay, shared memory. Okay, even we are working in parallel with some few, okay, processors. In the end, we are sharing the same. Okay, we are sharing the same memory. And if you remember in chapter 2, I think, or 3, we said how when we have, okay, multiple access for the memory, we lock and unlock. If you remember, okay, how to lock a value then unlock it. Okay, this is what we're calling synchronization. Okay, so memory access time, okay, uniform, non-uniform. So we can see we have n processors, okay, as a cache, okay, interconnection network, and we share one, okay, memory. So when any processor accessing any memory, it must be the synchronization between them using, okay, locks. Okay, this topic already addressed before in previous chapters, how to lock and how to unlock.
Dr. Al-Final عنا all the chapters.
It's a comprehensive, but we have to concentrate on the last, I think 4, 5, 6 more. Okay, chapter 6, as we can see now. Okay, we have only the 2 or 3 formulas in the beginning of this lesson. Okay, you have to just see the examples, and later on I will send you on WhatsApp. I'll send you some exercises, or on a blackboard I will put some exercises for you so you can have a look at them all as a revision. Okay, and also in chapter 5 we can say also I talked about the memory and the Hamming code and all this. Chapter 4, if you remember, we talked about, okay, the control, how data flow through, okay, the processor using, if you remember, the fetch, okay, decode, execute, memory, and write, okay, write into memory. Okay, يعني هدول
دكتور لأنه لأنه الصراحة يعني هو ما خصك أنت بس، لأنه كتير راحوا علينا من وراء الفرص يعني. حاسس نحن we're just able to solve problems بس كل شيء definitions و theory يعني
انت
كتير
theory definitions listen theory definitions مثل ما
يعني مش
نحن انت you are responsible يعني about the slides that you have. Okay, وانا يعني don't be afraid of any, don't scare from anything. انا I will be with you until امتى exam 17 Wednesday 17 at 8 a.m.
Yes.
يعني أنا I will be available
ودكتور
from now to 8 a.m. on Wednesday 17th for any question you have anytime. So yeah, welcome to ask me anytime you feel you need any support. Okay, but in general, problem solving is a problem solving. Well, and I gave you some examples. So we work out some exercises, and however, for the if you remember, أنا بالtwo tests في عندي كان في exercise يمكن true or false أو ما بعرف multiple choices. يعني هيدا بيكون هو أكثر يعني عن نعمل selection للmain terminology used يعني مش حنقي أنا اوكي تفصيل صغير ونجي نسأل عنه اوكي حنحكي مثلا انا قلت شو different between الفيكتور والسكالر. الفيكتور إنه مثلا processor مثلا the vector processor used okay to access okay sequence of data elements okay in the same time, which is used for parallel programming or parallel processor. However, a single data access it's okay only for scalar. يعني
دكتور سوري
yes yes
يعني انت اللي حتحط لنا الفاينل اكزام.
هلا انا اساسا we're still arranging with the course coordinator and Dr. Ruwaida. Okay, حيكون في contribution from all of us. Okay, but we try to get the best version for you. Okay. Okay,
Thank you دكتور.
I repeat again, أنا available until 8 a.m. on Wednesday. Okay.
Okay,
All
thank
right,
you.
so you're welcome to ask any question even on WhatsApp or send me email or okay. هلا هون انا just
هو الدكتور لأنه شو اسمه يعني لأنه اضطرينا نقطع السلايدز كتير على السريع يعني ما بعرف أذاكر بس في سيشن مثلا عملنا شي 40 سلايدز على السريع يعني نحن كثيري there is no way that we يعني time wise إنه to assimilate وكل chapter شي 100 سلايد
هلا هن الشابترز
يعني
هن
لأنه
بيج
كتير راح علينا وقت.
هن البيج شابترز فعلا يعني هن especially هو الشابتر I think chapter 4 and chapter 5 هن big chapters صحيح. هلا هيدا it's only chapter 6 is only about 50 I think 55 slides. Okay أنا already I put on Blackboard chapter 4 and 5 I think they already there. I'm not sure chapter 6 هلا I'll check if I put it or not. But on chapter 6 اوكي مثل ما عم نقول هيدا يعني في يعني اكثر work on the first part على ال speed up with time. Okay, then definitions هن big chapters that you know, that's how it is. We have to go for it. Okay. You know, if in one day just read these slides and you know understand the main terminology, that should be okay. Okay.
I know إنه هو البروجرام هيك بس أنا قصدي يعني مثلا حتى لو 50 سلايد ما كل سلايد فيه definition
صحيح.
يعني ونحن قطعنا عليهم كتير على السريع يعني we have over ما بعرف شي 100 definitions